Okay, so let's get started. In this session, what I'd like to do is to cover some of the very simple algorithms that are used for finding roots of equations. And I'm going to show you, I'll also discuss code for two of them. And I would like you to try and, on your own, write the code for the third algorithm that we will discuss. I will put in the code in the notebook that I will upload, but you should try it as an exercise yourself first. Okay, before we get into things, does anyone want to ask any questions or make a comment at this point? Okay. Okay, so one thing I'd like to show you in these notebooks is that if you have a cell, okay, so you'll forgive me if you already know everything about Jupyter notebooks. If you don't, then maybe this information will be useful to you. If you have a cell and there's a number of choices, you can mark that as being a cell for code, or you can say, for example, that this is a cell for text, and then you want to use Markdown. Okay, so if you're using Markdown, and then you can use, if you want to use that cell for a heading, then you can use one hash symbol. So I've written a hash symbol, and then I've written about Markdown. Now if I hit run, it gives me a heading like this. Okay. If I wanted it smaller, then I'd say, all right, here's two hash symbols. And then if I run it, I get a smaller heading. Okay. So let's set that back to where it was. So one hash symbol, write what you want for your heading, in this case about Markdown, and then you hit run, and then you've got yourself a heading. Now, if you want ordinary text, just write the ordinary text in to your cell. Again, the cell should be set to Markdown rather than code in your notebook. Right? If you set it to code, this is what happens, and it thinks that you want to run this as a code. If you set this cell setting to Markdown, then it just looks like text. Then if you hit run, you'll get a text. So Markdown for text, and then hash symbols if you want headings. The more hash symbols you use, the smaller your headings are going to be. Okay. Also, if you're used to using LaTeX for math symbols and math fonts, assuming that you already know how to do that, and then you put your math symbols between single dollar signs if you want them inline, and you put them between double dollar signs if you want a display. So for example, if I write DJ is equal to 0 with between single dollar signs, that means put it in math fonts and put it in this line. And if I want to write D star J equals 4 pi I using math fonts, then I will put that between double dollar signs, and that would mean set it off separate from the text as a display form. Okay, so if I hit run, then and this is what I get. So, okay. All right, so a little bit of preliminaries about formatting Jupyter notebooks. Now we move on to some root finding methods. One method that we use is the bisection method. I'll discuss its advantages and disadvantages later, but first let's discuss what the method itself is. Okay, so the bisection method. it makes sense when you consider the intermediate value property or the intermediate value theorem. Okay, so that says that if f is a continuous function, so it's a continuous real valued function on the closed interval from a to b, that means including a and b, and then f takes all the values between f of a and f of b. Okay, so if f of a is -1 and f of b is 37, then at some point f takes all the values between -1 and 37. Okay, this is depending upon f being continuous. So if f is taking a jump, if it's some sort of a step function on that interval, then this you can't apply this intermediate value property. Okay, so the corollary of that is that if f is continuous on a to b, including a and b, and okay, so there's a problem. So let me fix that. If f is continuous on closed a b, and f of a and f of b have different signs, then f has a root on the interval from a to b. Okay, so if f is negative on one end of the interval and positive on some end of the interval, then at some point f takes, if f is continuous on the interval from a to b, then at some point f takes the value 0. So there is a root somewhere between a and b. Okay, so then the idea of the bisection method is this: start with some interval ab, closed ab, with your continuous f taking values of different signs at the endpoints. Now evaluate f at the midpoint. If f of c has the same sign as f of a, then that will be your new a. That will be your new left endpoint of a new interval. If f of c has the same sign as b, then that c will be the new b. It'll be the new right endpoint of the interval. So what will happen is that as you iterate through, your intervals are going to decrease in length by a half each time. Okay? So you keep having the search, you keep having the search interval a to b until the absolute value of f of c is less than some tolerance. Okay? So for example, let's say I have f of x equals x cubed plus x plus 1. That's going to be my, I want to find a number, c, such that f of c is equal to 0. Okay? Now, maybe I draw a graph and I see some interval where over which it takes negative values and positive values. Okay? So if I look, I see that f of -1 is equal to -1, which is less than 0. And f of 0 equals 1, which is greater than 0. And how do I know that f is a continuous function? From -1 to 0? How do I know that?
So it's a polynomial, that's
right.
why.
Right. Polynomials are continuous everywhere. So in particular, it'll be continuous from -1 to 0. So then this corollary to the intermediate value theorem says that, okay, at one end it was negative, at the other end it was positive, somewhere in between the value must be 0. Okay? So it makes sense to go looking for that. And you know, if we were writing a careful code, we would say, all right, you input the interval. And then we would say, oh, well, we would check. We would make sure that it actually has different signs. The value of f takes different signs at the endpoints. We should actually check this. I didn't do that, but a careful programmer would have checked this before running the algorithm, okay? All right, so let's do a numerical experiment. We set the tolerance to 10 to the minus 5, and we do 10, and then we use this interval from -1 to 0. And if we do 10 iterations, we'll get this root of about -0.68. Okay. All right. So before we look at the code, the advantages of the bisection method. Well, it's really simple. It just keeps plugging away. The size of the interval keeps decreasing by a half. And it keeps plugging away without breaking. Okay. Disadvantages are that it's going to be very simple. It's going to be very slow in comparison to some other methods. Okay, so over, say, compared to the Newton's method, which we'll discuss next, this could be rather slow. Okay. The other thing is it's inherently one-dimensional. The other methods that we're going to discuss in this session have higher dimensional analogs, right? But this one will only work in one dimension. Okay. Okay, so let's try a code. Okay, when you're writing your code, make a comment and say what the code is actually going to do. Now we need we need to be able to evaluate the function values at A and at B and at C, right? So we have to define the function. def means I'm going to define a function. The name of the function is f. It takes an input x. And then what should it do? Well, it should calculate x cubed plus x plus 1, and it should return that value. So I say return x cubed plus x plus 1. Okay. We will also need the original endpoints of the interval, and then the interval is going to be cut in half each time. So let's say that the original interval will start at -1, at A is equal to -1, and end at B is equal to 0. The original length of the interval will be B minus A, and that will decrease by half as we go through. Okay. I don't know what FC will stand for, f of C. I don't know what it is, but I just I need some number for it, so I'll put in 10.0. Or I could have put in the actual value, right? I could have calculated C and then put in the actual value. Okay, and I want to count how many iterations that I'm doing before this thing terminates, right? I may, again, if I'm a careful programmer, what I should actually do is I should have something that kills the program if it takes more than a certain number of iterations. Okay. Okay. So now my tolerance will be that the absolute value of f of c should be less than 10 to the minus 5. So then I'll say that I want you to keep going through the algorithm as long as the absolute value of f of c is greater than 10 to the minus 5. Okay, fine. Now let's run the algorithm. C is the midpoint, so 0.5 times a plus b. FA equals f of A, FB equals f of B, and f of C is the value at the endpoint. Now, what did we say? We said that if f of C has the same sign as f of A, then let C be the new A. If f of C has the same sign as f of B, let C be the new B. Okay, so that's what we say here. This is how we check if signs are the same or if they're different. If they're different signs, when you multiply those two things together, you'll get less than 0. If they're the same sign, you will get a negative times a negative or a positive times a positive. You get something that's bigger than 0. Okay, so if f of A times f of C is greater than 0, then A is equal to C. Otherwise, else, colon, let B equal C. Let's count what iteration we're on. And, right, increase the number of iterations by 1. Print the iteration, print the midpoint value, and print your f of C, and decrease the length by 1/2. Okay. And if we run that, then as I said, it goes through 10 iterations. The value of f of this number is like 1.28 times 10 to the minus 6. And the value is, the approximate root is minus 0.6823 or so on. Okay. All right. Any questions about that one? Yeah?
Yes, sir. So I wanted to ask, sir, what role does length play here? We are using length.
Oh, yeah, it doesn't really play a role. I just would like to see, I suppose I could have just calculated at the end, right? I could have just said 0.5 times to the number of iterations times the original length. It might have been more efficient to do that. But I just wanted to see how big the intervals were as I went along. I don't actually need them to do the result. Okay.
Yep.
Right. Any other questions? All right. Next one would be Newton's method. Some people call this the Newton-Raphson method. Okay. Now, this is used to find f of x is equal to 0, assuming that f is differentiable near the root. And as we're going along, we have to keep finding, we either have to find or we have to estimate the derivative of f as we go along. So each iteration is more expensive than the previous method. And you're assuming the existence of the derivatives near the root. Okay? So the idea of Newton's method, x is the guess for the root, and I'm going to use the notation that x star is the actual root. Okay. So x star is the actual root. Now, remember Taylor series, right? The Taylor series says, now think of x star as x plus h. Wherever you are, plus h takes you to the actual root. So f of x plus h is f of x plus f prime of x times h. H is the difference between x star and x. Plus 1/2 f1 over 2 factorial f double prime of x times h squared plus, and h terms in h cubed, h to the 4th, and so on and so forth. So you have this infinite Taylor series, right? Okay. So we're going to use this Taylor series to come up with an algorithm. Okay, so we'll make this approximation. If I'm close to the root, then the distance x star minus x is small, and the distance x star minus x squared is really small, hopefully. So I can ignore the squared terms. So I will get that f of x star is approximately equal to f of x plus f prime of x, x star minus x. Now x star was the root, so f of x star is 0. So I should have that 0 is approximately equal to f of x plus the derivative of f at x times x star minus x. Now, let's rearrange. Let's solve for x star. If I do a bit of algebra and I solve for x star, then I get that x star is approximately equal to x minus f of x divided by the derivative of f at x. Okay? Well, okay, so that's how you would linearly approximate the actual root. If you're starting from x, this is the linear approximation for the actual root of the function. Okay. All right, now we're not going to get the actual root, right? Because it was an approximation, not the exact Taylor's formula, which had infinitely many terms in it. But hopefully you get a better approximation than the original guess. So what do? Then that new estimate that you got, that's your x now. Now you do it over again and you do it over again. And you get a bunch of iterates. So basically, the n plus 1th approximation is the nth approximation minus f at the nth approximation divided by the derivative of f at the nth approximation. Okay. All right, so let's do an example. We're going to take the same function that we had before. So that's defined by f of x equals x cubed plus x plus 1. Let's take the tolerance to be that I'm going to stop when I have an x such that the absolute value of f of x is less than 10 to the minus 5. I have to start somewhere, so let's start at 0 is my initial guess. Now what's the result? 6 iterations will give me basically the same result that I had before. Okay, so 6 iterations instead of 10 looks like an improvement at the cost of each iteration being more expensive than the previous algorithm. Okay. Now, the convergence is very different. The convergence to the root is very different. If it actually converges, you will get quadratic convergence. So if f is actually twice differentiable and x star is the root, and you've got some interval about the root, x star minus delta to x star plus delta, and your f of x is not equal to 0 within that interval, and your second derivative is bounded on the interval, then the error of each iterate goes as the square of the error of the previous iterate. So if you've got a reasonable guess for a reasonable function, then it will get to a good approximation of the root very quickly. Okay, much more quickly than in the previous one. Okay, but if we want to discuss a little bit more and to see how things can go wrong, then remember we came up with this from a Taylor series. So let's go back to Taylor's theorem. Okay, So Taylor's theorem says that if you have f and its first n plus 1 derivatives are continuous on an interval containing a and x, then f of x equals f of a plus f prime of a x minus a squared plus and so on, up to the f of the nth derivative at a divided by n factorial, plus some remainder term. Okay? And the remainder term looks like 1 over n plus 1 factorial, and the n plus 1 derivative evaluated at c times x minus a to the n plus 1 for some c on the interval between a and x. Okay. So this is interesting to us because it's going to tell us something about how bad things can get. Okay? So one thing is that for the second, if this was the second derivative, we would have 1 over 3 factorial. Sorry. The remainder for the second derivative would be like 1 over 2 factorial second derivative times c x minus a to the 2. So what happens if second derivatives are really large? Then this remainder term could be really big. Okay, so that could be one thing, right? Maybe it looks like a sensible function, but when I take its second derivative, that gets to be really large. Okay. All right, so you might want to think about an example, coming up with an example where that happens. Okay. Now, what if the first derivative is small? Right. So first derivative is close to 0. Then what happens? Well, let's go back up here. Right? We've got xn minus f of xn over first derivative at xn. But the first derivative is really small. Right? So you could be subtracting off a really large number. You know, 1 over a very small number is a very large number. And so you could end up taking too big a step and ending up very far from the root. Okay? And the other thing could be that the first derivative exists away from the root, but at the actual root, it's undefined. Okay? So if you're trying to find a root of x over, okay, perhaps I should leave this as an exercise as you're trying to find a root of x to the 1 over 3 using Newton's method. Think about what would happen and then test it out. What if the root is a local max or min? Well, that's like the case of, right, if the root is a local max or min, think about what's happening. You're taking a step, and then you'd be taking a step back, and so on and so forth. So you can get oscillations. And the other possibility is, what if the guess is very far away? You could probably end up wandering around a lot. Okay? All right, so Newton's method is more powerful. If you're close enough to the root when you take the initial guess, then your convergence will be quadratic. But you have these issues that could happen, for example. So that when Newton's method goes wrong, maybe you should think about it, or perhaps you should think before you do the problem that if there's a possibility, for example, that your root might be close to a local maximum or a local minimum, for example, or that think about what the values of the derivatives would be, right? Take a look at both functions, the actual function and the derivative of the function, and see if the region where you're looking in, maybe the derivative is really small, okay? All right, so take a look at the code. We need this derivative. Sorry, we need the actual function. You have to return x cubed plus x plus 1. We need its derivative. I'm calling that function for finding the derivative fp. So now you need to return 3x squared plus 1. That's the derivative. Okay, I'm going to start an initial guess at x is equal to 0. And I'm going to use the terminology that fx means f of x, starting with the 0th iteration. So while the absolute value of f of x is bigger than 10 to the minus 5, that's my 10 to the minus 5 is my tolerance. Fx equals f of x. Fp of x, the derivative, is fp of x. And now the updated guess is x equals x minus f of x divided by fp of x. Let's keep track of how many iterations we need. And we're going to print the iteration, the approximation, and the value of the function. And if I, where did that go? If I run this, then I've got 6 iterations. And again, quadratic, what did that mean? The error here was like 10 to the minus 5. The error here is like 10 to the minus 10, right? So extremely fast convergence compared to the other one. Okay. So are there any questions so far? Okay. Now, I would like to discuss things for which I'm not going to give you the code, or at least I'm not going to give you the code right away. And I'd like you to try doing the problem yourself. I mean, try doing the coding yourself before you, before I give it to you, or before you look at my code, okay? All right, so fixed point iterations. The idea is that you frame the problem as x equals g of x, and you iterate as x sub n plus 1 equals g of xn, where the xn, where xn is the nth estimate of your root. Okay. So for example, tangent of x minus x is equal to 0. I want to solve this. Now, how can I set this up as a fixed point iteration? How would I do that?
X equals tan x.
Yeah, x equals tangent of x, right? So x equals tangent of x to the n. Okay, what about this one? X of x divided by 2 minus the sine of x is equal to 0. How can I set this up as a fixed point iteration? Xn plus 1 is equal to what of xn?
2 sine x.
Right, 2 sine of xn. Right? Okay. All right. So I will start from, if I start at x equals 1.9, and that's, well, I'll graph the function first, right? Because I need to be able to guess some initial estimate, right? So if I start at x equals 1.9, after 16 iterations, one way of setting the tolerance is to say, how much are the iterates changing? So let's say that I say that the iterates are changing by less than 10 to the minus 5. Then I can stop. Well, if I do that, then I get this 1.8955, right? Okay. Now, I'd like to discuss how the error goes. Okay, how is the error changing? So the first term has an error, the next term has an error. How much is the error decreasing? Okay, so let's say that my error, the error on the n+1 iterate is equal to the difference between the n+1 iterate minus x star. X star is the actual root of the function. Okay. Now, how did I get x of n+1? That was g of xn. Okay. Minus g of x star. Now, remember, this is a fixed point iteration. So if I get exactly the root, then x star is equal to g of x star. Is that okay? All right. Now what am I going to use? Whenever I set up something like this, what am I going to use? What's in my toolkit?
Mean value theorem.
Well, okay. Well, all right. Mean value theorem is a workhorse for this, for analysis. Yes, that mean value theorem is one possibility. What's the other possibility? The other possibility is the other possibility would be using Taylor series. Okay. All right. So the nth estimate is what? Well, it's the same as x star plus the nth error, the way I've defined the nth error. So g of x star plus en minus g of x star. Okay. Now, as I said, we're just going to see Taylor over and over and over again, right? So, okay. So this is what the n+1 error was. Now, what's this? Remember, g of x star plus en is g of x star plus the derivative of x star times en plus terms in en squared. Okay? So if I take this, put this in here, and I subtract all of the order of n squared terms, right? I just shove them all into this O of en squared. All the other infinitely many terms in the Taylor series, I just shove them into there. The ones which have en squared, en cubed, en to the fourth, infinitely many terms, I just shove them into this big O notation, okay? And what I'm left with is en g of x prime, g of x star, g prime of x star, okay? Now, what does this tell me about errors increasing or decreasing? What do I want? Okay.
So it's decreasing?
What? What's that?
It's decreasing, sir? The error is decreasing?
When is it decreasing?
Because
I want it to be decreasing. What do I need for this to be decreasing?
This expression is going to reduce the error, is it?
When is it going to reduce the error? Under what conditions will the error be decreasing?
Because the scale of point value is always lesser than the point values. No?
So as long as the derivative of g and en are less than 1,
yeah,
then the error will decrease.
So Let's suppose that the error is small enough. Let's suppose that the error En is small enough that En squared is really small. Then all the other terms, infinitely many terms, are also very small. So I can make the approximation, if I'm close enough to the actual root, I can make the approximation that En plus 1 is approximately equal to En times G prime of X star. So if I want the magnitude of the error to be decreasing, then I want to multiply En by something whose magnitude is less than 1. If I multiply it by something whose magnitude is bigger than 1, the error is actually increasing. The magnitude of the error is actually increasing. Okay? So En plus 1 is approximately equal to the derivative of G at the root times En. So if the derivative of G at the root is less than 1, it converges, and it's a linear equation. So we say that it converges linearly. And if it's bigger than 1, if magnitude of G prime at the root is bigger than 1, then it is increasing. Okay? And then we'll have divergence. Okay? Okay. So here's an example. I want you to estimate the solution to x to the 4 minus x minus 10. I want you to make that, tell me what x makes this equal to 0. And I think that that x is near x is equal to 2. Now, what if I set this up? What if I say that my fixed point iteration, I can solve for x, so I can get x is equal to x to the 4th minus 10. So I'm going to let my g of x equal x to the 4 minus 10. Can you tell me what's wrong, based on our previous analysis, can you tell me what's wrong with that fixed point iteration?
So the derivative of g of x near 2 is large.
Yeah. If I suppose that the root is actually near 2, then I might be able to reasonably suppose that g prime of x star might be approximately equal to g prime of 2. But g prime of 2 is, let's see, 4x cubed. That's 4 times 8 is 32. That's much bigger than 1. It has absolute value much bigger than 1. Yeah, so there's a high, yeah, so no, that's not going to work, right? Okay, now an alternative to that is to say that, well, x to the 4th is equal to x plus 10. So x is equal to x plus 10 to the 1/4. Okay? So that's your fixed point iteration. Feed me in an initial x near 2, and then I'll replace that by x plus 10 to the 1/4. Can you tell me if that makes more sense? What's g prime near 2? Well, what's g prime at 2, in fact? Exactly at 2. well, it's 1/4 x plus 10 to the minus 3/4, right? And you should, well, okay, so you do the analysis, all right? Okay, now Newton's-Raphson also works for multiple variables. Fixed point can also work for multiple variables. Remember, bisection method is not going to work. Okay, so let's do a fixed point method with two variables, okay? So we have a system of equations, y equals x squared, and x squared plus y squared is equal to 1. So how would you estimate where the solutions are? Well, I draw a parabola, y equals x squared, then I draw the circle given by x squared plus y squared equals 1. I'd see where the two things intersect, right? I can graph both of them. And so I can get a reasonable estimate, at least for starting guesses, of the for the estimations. Okay. All right. So graph to see two solutions. Now, if I do this, I want a fixed point. What does the fixed point do? Before we had x is equal to g of x, right? So a fixed point with 2 points might be something like x is equal to h of xy, and y is equal to k of xy. Okay, so I go back to my system and I look around and I say, okay, I can do a bit of manipulation, and I can get that x equals root of 1 minus y squared is one equation, and y equals x squared. So x is a function of x and y is a function of x and y, and maybe that system can help me find a solution. Iterating that over and over again can help me find a solution. Find an initial x and y, and then update the x and y by using these right-hand sides over here. Is that okay? You can ask a question if you need to. Okay, so like I said, if you graph it, you'll realize that the solutions are on the unit square. You probably have to now, as I said, these are very standard algorithms, so you're going to find libraries or packages that have these algorithms coded for you. You should, there's a educational academic value in you coding of the simpler problems for yourselves before you start relying on packages or libraries. Okay, so we look for solutions on the unit square. Okay, and this is the map now. Okay, take your x and y and replace them by new x and y. X is replaced by 1 minus y squared, and y is replaced by x squared, and that is my fixed point iteration. We repeat that over and over again. Okay, and the result is not good. If I do that, I start with x equals 0.5, let's say, and I start with y equals 0.5. And after 33 steps, it's bouncing, the results are bouncing between the corners of the unit square. Okay. Now, yeah, there's a question?
Sir, yes, can you please repeat this last part when you said that it bounces across the unit square?
Yeah. Sorry, repeat your question, please.
I didn't get this last part when you said that the value keeps on bouncing between the corners of the unit square.
Yeah, so it just, okay. So forget about the corners business, just the values you get are bouncing back and forth. You're not sort of settling down to, doesn't look like it's settling down to one fixed point. Okay?
Okay.
Okay, so now, there's a theorem called Brouwer's fixed point theorem. It says that a continuous mapping, okay, these mappings are continuous, of a convex closed set onto itself has to have a fixed point. So the unit square is a convex closed set. So it has there is a fixed point. We don't seem to be finding it in the way we've set things up. Okay, and again, you go and you code this yourselves, okay, and verify, right? Don't just believe me because I'm telling you, okay? Verify that this is the behavior that you get. Okay, and all right, so let's take a look at the derivatives. And from, hopefully from Calculus 2, you remember something called the Jacobian? Is that right?
Yes, sir.
Yeah, okay.
Not from Calculus 2, but from another economics course.
Oh, okay, all right. So, all right, so what's the definition of the Jacobian here? What's this zero term? Where did that come from?
From the derivative?
Yeah, so that was the derivative. Okay, so we had these two functions, right? So this is the Jacobian of this f, okay? So the way you get the terms of the Jacobian is you say the derivative of this first term with respect to x, then the derivative of that term with respect to y, then the derivative of this second term with respect to x, then the derivative of the second term with respect to y. So you should confirm that this is the Jacobian that you get. Okay? And now if you calculate the determinant, so this is a matrix, it has a determinant, and if you calculate the determinant at the solution to this system, okay, and we can get that to a, we'll see that the determinant is bigger than 1. Okay, so this is sort of analogous to this idea that we had before, right? There we said that the derivative, its magnitude should be less than 1. You have divergence if its magnitude is bigger than 1. So in the multivariable calculus, the sort of the equivalent idea is you look at the sort of the derivative that matters here is the Jacobian. It's a kind of derivative. And the determinant of the Jacobian is a measure of how big it is. So if you were to put in the values of the actual root, the values for x and y, and calculate the determinant of this Jacobian, you would get something that's bigger than 1. Okay, so once again, you're going to have you're going to have divergence. Okay. So, all right, then we say, look, let's do something else. If we go back to our original system, we can set up another kind of fixed point iteration. And that fixed point iteration would be g of xy. X is replaced by root of y, and y is replaced by root of 1 minus x squared. Now we calculate the Jacobian for that. Okay, so if we implement that, we get these two values for x and y. And if we take a look at the Jacobian, this is the Jacobian at the solution to the system. And if we put in this value for x into the Jacobian, you'll see that the determinant of the Jacobian is less than 1. Okay? So is that all right? Okay. All right, so now, hopefully we're going to be, we want to be able to do our Newton's method and our fixed point methods in higher dimensions. And when you're doing things in higher dimensions, you need matrices which are called Jacobians and Hessians, depending upon the order of the derivatives that you want. Okay, so we need to, just in case you haven't covered this stuff, just do a very elementary review of higher dimensional mappings. Okay, so we have the idea of a limit in higher dimensions. So x here is a vector, okay? And x naught is a vector. And let's say we're mapping to the real numbers. So we have the idea of a limit in higher dimensions, okay? Which is analogous to the idea of a limit in one dimension. Okay. We have the idea of continuity. Also, if the limit as x goes to x naught of f of x is the same as the function value at x naught, then the function is said to be continuous at x naught. Okay. And remember before, if a function was differentiable at x, then it was continuous at x in one dimension. Well, here, sort of the analogous result is that if partial derivatives of f are bounded near x naught, then f is continuous at x naught. Okay. Now we can also have maps from, say, Rn to Rn. Okay. So we feed a vector x into f, and it gives us back n values, f1 of x, f2 of x, up to fn of x. So the small fi map from Rn to R. Okay. And again, we can have the idea of a limit. Basically, this means that f of x has a limit L at x naught, means that as x gets very close to x naught, the function f of x gets very close to L. Okay. Okay. So that means that each one of these fi's is also nicely behaved. Each one of these is approaching some limit. And we also have the notion of continuity, right? F is continuous at x naught if the limit as x naught is the same as the function value at x naught. Okay, and the thing that we're going to end up using is the Jacobian, okay, and determinants of the Jacobian, okay. So the Jacobian, if you have this f, which is mapping from Rn to Rn, the Jacobian is a matrix of partial derivatives of f evaluated at x. Okay. Okay. So you evaluate each one of the of those fi with respect to xj, and that will give you the Jacobian. Okay. Actually, what I should do, I should have given you a few examples of just calculating Jacobians just so you get used to it. So I'll add those to the notebook that I'm going to update. Okay. Let me give you the idea of a fixed point method. Okay. So I have a bunch of equations, right? F1, F2, Fn, they're functions of variables x1, x2 up to xn. And I would like to get all of them equal to 0. Then in vector form, I need to solve some f of x is equal to 0. And then the fixed point method would be rearrange this f of x is equal to 0 so that you get g of x is equal to x. Okay? Then what do you think we're going to be hoping for? Here, x is a vector, remember, is an n-dimensional vector. We set up g of x is equal to x. What should we be looking for to see if we have a hope of convergence?
So the determinant of the Jacobian should be 0, or should be less than 1.
Yeah. The determinant of the Jacobian of g near the root, near the desired function, the fixed point, should be less than 1. Okay. There should be some number less than 1. Okay. And if you're starting off in a region D, which is close enough, then you're going to converge to the fixed point. Okay. So I would like you to return to the example and make an argument from the Jacobian to explain the results. Okay. So enough for today. I will add some codes for fixed point methods, but I want you to try writing those codes first before you check my code. Okay. And then we'll see the use of a library called SciPy, where a lot of these common methods are already available for you, and the code is nicely optimized, right? But there's an academic value in you writing 2 or 3 of them yourselves before you start relying on packages or libraries. Okay. Are there any questions? Yeah?
Sir, actually, I wanted to make a request.
Yeah.
I just checked that you uploaded the Python notebook, the Jupyter notebook on LMS Labs, which is the new model, I guess.
Yeah.
So the file uploaded on that is not very user friendly. I just wanted to request if you can upload it on the LMS, which is the, I don't know how to differentiate between the two. There is this one LMS that has the resources and everything.
Yeah.
And there is this other LMS which has the current lectures and stuff. So the already uploaded file isn't very user friendly and not even downloadable. So
okay, I'll try to do that over the weekend. Okay. All right.
Thank you.
Thank you. Okay, then I will see you on Wednesday.